Hi everyone. In this video, I would like to give a small presentation on typical CNN convolutional neural network architecture. Firstly, introduction to CNN architecture. Convolutional neural networks (CNN) are a type of deep neural networks designed for processing structured grid data such as images. CNNs are widely used in computer vision tasks such as image recognition, object detection, and image segmentations. The architecture of a CNN typically consists of convolutional layers, polling layers, and fully connected layers. Convolutional layers are the building blocks of a CNN and are responsible for extracting features from the input data. Each convolution layer applies a set of filters to the input data to detect the patterns and features. The output of a convolutional layer is called a feature map, which represents the presence of different features in the input data. As we can see, the image of the convolution neural networks, which consists of layer 1, layer 2, and the classifier. Now, convolution layers. In convolution layers, there are three types of layers, which is input layer, hidden layer, and the output layer. The input layer. It is the layer in which we give the input to the model. The number of neurons in this layer is equal to the total number of features in our data, number of pixels in the case of an image. The second one is the hidden layer. The layer which lies between the input layer and the output layer is called as the hidden layer. The input from the input layer is then fed into the hidden layer. There can be many hidden layers depending on our model and the data size. Each hidden layer can have different number of neurons which are generally greater than the number of features. The output from each layer is computed by matrix multiplication of the output of the previous layer with the learnable weight of the layer, and then by the addition of learnable biases followed by the activation function, which makes the network nonlinear. Output layer. The output from the hidden layer is then fed into a logistic function like sigmoid or softmax, which converts the output of each class into the probability score of each class. CNN architecture. The convolutional layer applies filters to the input image to extract features. The pooling layer downsamples the image to reduce computation. And the fully connected layers make the final prediction. The network learns the optimal filters through backpropagation and gradient descent. Pooling layers are used to downsample the future maps generated by the convolutional neural networks, convolutional layers. Common pooling operations include max pooling and average pooling, which reduce the spatial dimensions of the future maps. Pooling helps to make the network more robust to variations in the input data and reduces the computational complexity of the network. This is the CNN architecture, which consists of this is the input, this is the output, and all the layers which lies in between the input layer and the output layer is known as the hidden layer. Now let's see how convolutional layer works. Convolutional neural networks or convents are neural networks that share their parameters. Imagine you have an image. It can be represented as a cuboid having its length, width, which is dimensions of the image, and height, that is the channel as images. Generally have red, green, and blue channels. Now imagine taking a small patch of this image and running a small neural network called a filter or neural on it with say k outputs and representing them vertically. Now slice that neural network across the whole image. As a result, we get another image with different widths, heights, and depths. Instead of just RGB channels, now we have more channels but lesser width and height. This operation is called convolution. If the path size is same as that of the image, it will be a regular neural network. Because of this small patch, we have fewer weights. Is the input source. The first thing is the input data. From input data, then it goes to the convolutional layer. After the convolutional layer, it goes to the pooling layer, then to the convolutional layer again to the pooling layer, and fully connected layers, and then we get the output. Let's see how convolutional layer works. CNNs are trained on large datasets using backpropagation and gradient descent. The model's performance is evaluated on a separate test set to measure accuracy and generalization. Techniques like data augmentation and transfer learning can enhance the performance of CNN models. Let's know the layers to build connects. A complete convolutional neural networks architecture is also known as connects. A coordinate is a sequence of layers, and every layer transforms one volume to another through a differentiable function. Types of layers. Datasets. Let's take an example by running a convent of an image of dimension 32 into 32 into 3. Input layers. It's the layer at which we give input to our model. In CNN, generally the input will be an image or a sequence of images. This layer holds the raw input of the image with width 32, height 32, and the depth 3. Convolutional layers. This is the layer which is used to extract the feature from the input dataset. It applies a set of learnable filters known as the kernels to the input images. The filters or the kernels are smaller matrices, usually in the size of 2 into 2, 3 into 3, or 5 into 5 shape. It slides over the input image data and computes the dot product between kernel weight and the corresponding input image path patch. The output of this layer is referred as feature maps. Suppose we use a total of 32 filters for this layer, we will get an output volume of dimensional 32 into 32 into 12. Now let's know the layers to build coordinates. Activation layer. By adding an activation function to the output of the preceding layer, activation layers add nonlinearity to the network. It will apply an element-wise activation function to the output of the convolution layer. Some common activation functions are ReLU, that is max of 0, x, tan h, leaky ReLU, etc. The volume remains unchanged, hence output volume will have dimensions 32 into 32 into 12. Pooling layer. This layer is periodically inserted in the conducts and its main function is to reduce the size of volume, which makes the computation fast, reduces memory, and also prevents overfitting. Two common types of pooling layers are max pooling and average pooling. If you use a max pool with 2 into 2 filters and stride 2, the resultant volume will be dimensional of 16 into 16 into 12. As we can see, the max pool with 2 into 2 filters and stride 2. From the first box, 1156, we get 6, as 6 is the maximum of this 4. And from the next box, from the 2, 4, 7, 8, 8 is the maximum, so we got 8 here. The next in 3, 2, 1, 2, 3 is the maximum number, so we got 3 here. And from the 1, 0, 3, 4, 4 is the maximum, so we got 4. This is the classification. This is the input layer. This both lies to the hidden layers, and this is the output layer. Advantages of convolutional neural networks. Good at detecting patterns and features in images, videos, and audio signals. The next is robust to translation, rotation, and scaling invariance. End-to-end training, so no need for manual feature extraction, and it can also handle large amount of data and achieve high accuracy. Coming to the disadvantages of CNN, computationally expensive to train and require a lot of memory, can be prone to overfitting if not enough data or proper regularization is used, requires large amount of label data, and the last one is interpretability is limited, that is it's hard to understand what the network has learned. Coming to the applications of CNNs, convolutional neural networks have numerous applications beyond image recognition, including object detection, facial recognition, and medical image analysis. They have been used in autonomous vehicles, surveillance systems, and natural language processing tasks. CNNs continue to drive advancements in artificial intelligence and are a key technology in the deep learning landscape. Coming to the conclusion, CNN architectures have evolved over the years for simple models like LeNet 5 to deep networks like ResNet. Understanding the components of a CNN architecture, such as convolutional layers, pooling layers, and fully connected layers, is essential for designing effective networks. By leveraging the power of CNNs, researchers and practitioners continue to push the boundaries of computer vision and